Okay, so today we're going to be looking at curve sketching. Now, curve sketching, the idea of what we're doing here is we're graphing an overall shape of a curve. This might not be and is in no way an exact science. We just want to see the overall shape of a curve using some common tricks that we've learned throughout the way. So a couple things we're going to label on each one of these. We're going to use the first and the second derivative test first to find maximum, minimum points. The second derivative test is going to give us points of inflection, where those concave up changes to concave down. And we're going to list any intercepts, relative extrema, and any asymptotes. So without further ado, let's go ahead and get started. So on number 1, let's get started with the easiest thing to find out. Let's find the zeros. Now, the zeros of any function is going to be where the top is set equal to 0. So this one, it's straightforward. X is equal to 0. Boom, we've got that. The next thing we want to find is any asymptotes. Now, what we're looking at here is I'm going to set the bottom equal to 0 because I know I can't divide by 0. So I'm going to say, hey, I know the bottom can't be 0. Now, we notice with this one, immediately x squared equals negative 1. I know that no matter what, unless we're looking at the complex plane, these do not exist. So I'm just going to go ahead and put does not exist because we're not really looking at lateral numbers here. So I've already got a few points that are going to be included on my graph. The next thing that we're going to be using is we're going to be using the first derivative test to find those maximum or minimum values. So let's go ahead and figure out what our first derivative would be. Looks like I got a quotient set up right here. So I'm going to set my top one as x. U prime would be 1. My bottom is going to be x squared plus 1, so v prime would be 2x. Now this, as I set it up, is going to be low d high minus high d low, all over low squared. So let's go ahead and get that moving. So low d high is basically going to be my x squared plus 1 minus high d low. So x times 2x is going to be 2x squared, all over low squared. So this x squared plus 1 squared. Now, this in and of itself might look a little complicated, but again, the first derivative, the biggest thing that we're trying to find here is we want to find those points, which means I'm really only concerned with the top. So if I set that equal to 0, so let's say, got to change that into an x squared plus 1 minus 2x squared. So that equal to 0. Let's see, so I subtract 2x squared, so that is a negative, not negative 2, that's going to be a negative 1, x squared plus 1. If I add that over, that's 1 equals x squared. And so the square root, which means positive or negative 1, is equal to my x. I have two maximum or minimum points, positive and negative 1. So we're going to take a pause on that. We're going to come back to this here in just a moment. After finding the first derivative, I want to find, okay, where does it change between positive and negative 1? So I'm going to use the second derivative to find those points, the points where it changes from concave up to concave down. So again, I've got what looks like a quotient rule. I know that this simplifies down to negative x squared plus 1. So I'm going to say my u is negative x squared plus 1. So u prime is negative 2x. V is going to be x squared plus 1 squared. V prime, we go ahead and use the chain rule shortcut here. So 2 x squared plus 1 times the derivative of that, which is going to be 2x. And again, we're going to set this up as low d high minus high d low, all over low squared. So low d high, I will get a negative 2x times x squared plus 1 squared minus high d low. So I've got this times all of this. So let's see, that's 2 times 2x. So that'll be a 4x x squared plus 1 negative x squared plus 1 all over low squared. So that x squared plus 1 was squared. Now it's going to be to the 4th power. And again, this looks really complicated, but I'm going to break it down into pieces. I'm going to take this top part and set that equal to 0. And the first thing, before I even begin, I notice that they both have an x squared plus 1. So I'm going to go ahead and factor that out. So x squared plus 1 is factored out. I also notice they both have a 2x that I'm going to factor that out as well and see what's left. So if I pull out the 2x and the x squared plus 1, I have a negative x squared plus 1. I pulled out the 2x, so I'm left with a 2. I pulled that out. Negative x squared plus 1. Boom. So I've got myself set up for 1, 2, 3 critical values here. The x squared plus 1 isn't going to pull anything because I know x squared can't equal a negative value, so that does not exist. The 2x is going to give us something. It's going to change at x equals 0. And then this, I'm going to have to go ahead and simplify what I can to see what it provides me. So let's go ahead and distribute in that negative. So negative x squared minus 1. Multiply that by negative 2, so that's plus 2x squared minus 2. Okay. So I get an x squared minus 3. X squared equals 3. So x equals positive negative square root of 3, which is roughly like 1 point something. Okay? So what we've got going on here is we have all the information we need to go ahead and sketch a graph. So let's zoom out just a tad and sketch our graph using this information. So now I know that on my graph, I have critical value right here at positive and at negative 1. I know I have 1 point something, so it looks like everything's going to fit between like 0 or negative 2 and 2. So I'm going to go ahead and say, if that's a 2 and that's a negative 2, that should give us more than enough space. So at negative 1 to 1, we've got something going on right here. So what I need to know is I need to know the orientation of the graph between these two values, because I don't know if this is a minimum or a maximum. I don't know if it's going up between these or down between these 2 points. So what I'm going to have to do is plug in some points around the edges, which means I'm going to come back to this original first derivative and plug in some values to the left of negative 1. So let's plug in like a negative 2. I'm going to plug in some values between there, so like a 0. And I'm going to plug in a value to the right, so like an f of 2. Okay. And so if I plug those values into this thing, let's go ahead and kind of work this out. So with the 0, that's going to be the easiest to figure out. That's going to be a 1 over 1, which is a positive number. So I know the graph is increasing from this point to this point. From this 0 to this 0, the graph's going up, which I believe would infer that this is going to be a minimum point. But let's check to make sure that the graph is going down, and if it's going up to this point, I should get 2 negative values on the other 2 edges. So if I plug in a negative 2, let's see, that's going to give me a 4 plus 1, which is 5. If I plug in the negative 2 squared, that's going to be 4 times 2, which is 8, so minus 8. And then if I plug in the negative 2 squared, it's going to be 4 plus 1, which is 5. Squared is 25. So that's going to end up giving me a negative value. So yes, the graph is decreasing on the left-hand side. If I plug in a 2, I know the fact that everywhere I plugged it in was a perfect square. So I'm going to end up getting the same thing right here, which means, again, I'm going to get another negative value. So what I've got going on here is I have the graph going down, then back up, then back down. And then at this point of x equals 0, it changes direction. And then at, let's see, right here and right here, it changes direction. Now, what do I mean by changing direction? The concavity changes. So if the graph is going down and up, what I know is going on right here is I have a minimum point. If the graph is going from up to down, what I have right here is I have a maximum point. And what I also know is that it's going to be in the other side of the axis because right here in the middle, we have our 0. And this makes quite the beautiful picture because I know between these 2 points, my graph is going to be concave down. So I get something that looks like that. I know between these 2 points, my graph is going to be concave. Actually, this is concave down. The other one was concave up. Oop, kind of curved too far down there. Okay. And then I know the graph is not going to touch the axis again, but it is going to change concavity, which means that at this point, it's all of a sudden going to deflect, and it's going to start curving like that. Same thing going on over here. It's going to change concavity at this point, but it's not going to touch the axis. So right here, it's going to change from that nice, pretty concave up to something that is concave down and slowly start going over. So we've got ourselves a nice little graph happening right there. Perfect. Let's do one. It's a little more straightforward. So with this one, we're going to take the same approach. I'm going to find the zeros, any asymptotes, use the first and the second derivative to pop through. So let's start number 3. So for the zeros, what I know is I'm going to set this equal to 0. So I'm going to have 3x cubed. And actually, this is a typo. This is going to be to the power of 4. So it's going to be 3x to the 4 plus 4x cubed. And I'm going to set that equal to 0. Now, when I factor out an x cubed, what I get is a 3x plus 4. So I get x equals 0 3 times, and I get x equals negative 4/3 once. Setting that equal to 0 and that equal to 0. So I get those 2 answers. And now this one might be a little confusing because, well, how does it equal 0 3 times? Well, let's go ahead and take a look at the first and second derivative before we make any other assumptions about that. The next thing is the asymptotes. There's no division going on in here, so they don't exist. We're not really worried about them at all. So let's go ahead and take a look at that first and second derivative. So if f of x, we're going to go ahead and do the power rule here. So 12x cubed plus 12x squared. I'm going to set that equal to 0. I immediately already went ahead and factored out a 12x squared, which means that I have, if I set this, I'm going to have x equals 0 twice. And again, I'm noticing there's something confusing going on. If I have a 0 multiple times, I have a maximum and a minimum point occurring at the same place twice, or maybe double max or double min. Not really sure how to interpret that just yet, but let's see how it goes. And then right here, x equals negative 1. Awesome. And then if I take that and move on to the second derivative, so f double prime of x, let's see, that's going to be 36x squared plus 24x. So if I set that equal to 0, I'm going to factor out a 12x, which is going to give me an x equals 0 and an x equals negative 2/3. Awesome. So let's take a look at the sketch of the graph and see what's going on. So again, I've got a lot going on between negative 4/3, negative 1, and negative 2/3. So realistically, what I could probably do is between negative 2 and 2, set most of these things straightforward. So first off, I know I have a point at 0 and at negative 4/3. So let's set that right there. My graph touches my axis at those 2 points. I also know that I have at 0 and at negative 1. I have 3 different regions in my graph. My graph's either going up, down, up. It's changing directions between these points. So what I'm going to have to do to see which direction the graph is going is I'm going to plug in values on each side of those intervals. So I'm going to plug in f prime of something to the left of that, which means let's actually plug in our point right there. Or no, let's just plug in a negative 2. Easier to calculate. something between those values. So let's say negative 0.5. And let's plug in a point to the right. So how about f prime of 1? And so we don't actually need to calculate that. We're just concerned with the sign, but let's go ahead and take a peek. So I know that with negative 2, that's going to give me an 8, a negative 8 times 12. I'm actually going to cheat just a little bit, and we're going to go ahead and crank this thing out. Okay. So what I've got is I've got 12x cubed plus 12x squared. And now realistically we could do this by hand, but we're just going to go ahead and say, what happens if I plug in a negative 2, a negative 0.5, and a positive 1? Well, I get a negative number, a positive number, and a positive number. Now, this right here might seem a little strange because I know my graph is going down, and then it's going up, and then it's going up again. But it should change inflection between those 2 points. So how does the graph go up and then keep going up? Well, let's take a look. Okay, so right here, it's pretty straightforward. It goes from decreasing to increasing, which means it's going down and then back up. So right at this point, so let's do this graph in red. So at this point right there, that's the minimum point. So it's going down and going back up. And then at this purple line at negative 2/3 is a change in concavity. So it's going to go from concave up, where it's a nice little bowl shape, to the other type of curve, where it's curving down. And it's going to curve down all the way until it hits that 0, where again it's going to change concavity, and it's going to start curving up once again. Now what we know is the fact that this increasing, we see the fact that my slope is positive and positive, so it's going up and up, and that change in concavity makes sense, which is why we saw this as a critical value. It's not a maximum or minimum necessarily, it's a flat point in the graph where it changes concavity and doesn't quite fully make that maximum or fully make that minimum. They're both shoved on the same part. And then right here, because there's no change in concavity, that just keeps going up, up, and away. Awesome. And so there we go. Now, what that's going to do is that's going to bring us to our next set of questions. The next set of questions are going to look like this. So why don't you go ahead, pause the video, try out number 5, unpause when you're done, and see how well you do. Same process, just a slightly different style question. Okay, so now that you've had a chance to take a look at it, let's go ahead and set up our zeros. So for my zeros, I know that either one of these, if x minus 1 is equal to 0, or if the natural log of x minus 1. This one gives me an x equals a positive 1. Nice number here. And if I rewrite this one as e to the 0th power equals x minus 1, anything to the 0th power is 1, so that's going to be 1 equals x minus 1, or x is equal to 2. Got 2 different zeros going on there. The other thing is we're going to look at an asymptote of sorts. I know that the natural log can't be taken of a negative number, so we're going to put this as a restriction. It's not an asymptote, but it is limiting the function in some way, shape, or form. I know that x minus 1 has to be greater than 0, which means x has to be greater than 1. So it looks like our 0 right here is going to be where our graph starts. But before we get beyond that, let's go ahead and find the first and the second derivative. So it looks like I've got a product rule going on here. So if u is x minus 1, u prime is 1. If e is the natural log of x minus 1, v prime is going to be 1 over x minus 1 times the derivative of this, which is just going to be 1, so that's it. And then the actual derivative itself is going to be set up like high. So it's going to be the natural log of x minus 1 plus high d low, x minus 1 times 1 over x minus 1. They're going to cancel out and turn that into a 1. And I'm going to set that plus 1 equal to 0 to find those maximum or minimum values. So natural log of x minus 1 is equal to negative 1. Let's see. E to the negative 1 equals x minus 1. If I add the 1 over there, that's 1 over e plus 1 is equal to x, which is equivalent to, and if we plug that in and see what roughly that is to help us graph, let's see, 1 over e plus 1, we get roughly 1.36. So we don't necessarily need to find the exact decimal place, but it is going to help us a little bit on knocking this problem out a little faster. Cool. So we've only got one maximum or minimum point. The next thing we're going to do is find those points of inflection. So f double prime of x, let's see, that's going to end up being 1 over x minus 1 times the derivative of that, which is going to be 1. So we've got that. And if I set this equal to 0, I'm going to run into a problem because I'm only looking at the top. And so when does 1 equal 0? So this graph does not change inflection. I have either a max or minimum point. No changes going on here. I also know that one of my zeros is my starting point. So let's, before we move any further, let's take a quick sketch at what's going on. If I know x has to be greater than 1, let's just go ahead and make this right heavy. And my first value at x equals 1, I'm going to go ahead and put an open circle at 1, 2, 3, 4, because I can't actually include that point. And then at 2, I will hit that point. And I know at 1.36, which is going to be roughly right about here, I have two different regions of the graph. But again, with my restriction, even though I have this full region over here, I'm not actually including any of this area over here. So I've got those 2 points. So I'm either going to curve up and go back down, or we're going to curve down and come back up. So let's go ahead and test to see what is the direction down here. So I'm going to plug in a point, let's say to the left of this. Now to the left of 1.36, we don't really have a whole lot of options here. We could plug in, let's say, f of 1.1, which will give us this value. And then we could plug in f of 2. Or not f of, f prime of. Okay. And so let's go ahead and pop this in there. So we have the natural log of x minus 1 plus 1. So if I plug in a value of 1.1 and of 2, we have a negative and a positive, which means this is decreasing and this is increasing. There's no changes in concavity. So the only way it can go from down to up is by having a minimum point right here. So the graph goes down and then comes up. And because it doesn't change concavity, it goes up at a faster and faster rate. Awesome. How'd you do? Okay. And so the last one, this one has a built-in domain restriction. So we're only going to be looking at this one from 0 to 2 pi. Why don't you go ahead, pause the video, try this one out, and see how you do. Okay. Now that you've had a chance to try it, let's give this a shot. Now, what you might have noticed is that right up front, we kind of run into a little bit of a problem here. I know the fact that with 2x minus 4 sine x, when I try and set that equal to 0, I don't really know a whole lot of values that would make this work because I've got an x in more than one spot. So I might try and say, okay, well, how about negative 4 sine x equals negative 2x? Divide both sides by negative 2, and I'll get 2 sine x is equal to x. But again, this doesn't really do a whole lot for me. So I'm going to put a pause in that and come back to that later on. I know with any sort of restrictions or asymptotes, I'm just going to go ahead and put a restriction. Outside of the 0 to 2 pi range, I don't see any division. I know sine isn't a quotient trig function, so I'm going to go ahead and assume that they don't exist. Which brings us to our first important part, finding the derivative of this function. So the derivative of this is going to be 2. Derivative of sine is going to be cosine, so 4 cosine of x. And I'm going to set this equal to 0. So that's going to be negative 4 cos x is negative 2. So when is the cosine of x equal to 1/2? Okay, so cosine of x equals to 1/2. This is going to bring us back to our unit circle. So I'm going to go ahead and say, okay, if I know cosine is adjacent over hypotenuse, that's going to be, when is my x over my radius 1/2? Well, I know radius always has to be positive, and if this is positive, that means I'm going to be over here in this area, where I have a radius of 2 and an x value of 1. And so that can happen either above the axis or below the axis. And this also looks a lot like a 30, 60, 90 triangle. So if that's the square root of 3, negative square root of 3, what we've got going on here is that this is a, let's see, opposite that is 30, so this is going to be a 60 degree. So I could either say 60 degrees, or more commonly, I'm going to say pi over 3. Also, if this is negative 60 degrees, well, let's see, that's 300, or that will be 5 pi over 3, not quite 2 pi. So I've got these two values going on right there. And then I'm going to come over here and do my second derivative. So f double prime of x. Derivative of cosine is sine. It's going to change the sign, so 4 sine x. And if I say, when does 4 sine x equal 0? Again, this is going to bring me right back to my unit circle. But this one isn't quite as complex. When does the sine of x equal 0? Well, we know sine is going to be opposite over hypotenuse, which is going to be the y value over r. So when is the y value equal to 0? Well, that's going to be right there, and again. So that's when x is equal to 0, pi, and 2 pi. And so let's go ahead and, ignoring what we got off to right here, let's see if we can't set up what the shape of this graph is going to look like over here. So keeping all this information in mind, again, I'm only dealing with 0 to 2 pi. So I'm really not worried about anything to the left of that. And I know, let's break this down a little bit more. If this is pi, and I have pi over 3, so 1, 2, there's my pi over 3, and there I have that. Okay, so I've got 3 different parts. I have pi over 3 and 5 pi over 3, where it's either a max or a min, So I would want to figure out what's going on between those. So let's plug in some values, quite literally, between the pi over 3 and 5 pi over 3. So I'm going to plug in f prime of, to the left, I'm going to plug in a 0. I'm going to plug in a value between them, so I'm going to plug in a pi. And a value to the right, so how about f prime of 2 pi? Awesome. And so if I do that, I could probably do this by hand, but we're going to go ahead and we're just going to speed up the process just a little bit. So I'm going to go ahead and set my function in there. So 2 minus 4 cosine of x. Make sure my mode is in right. I am in radians. Okay, good. So let's go back to the table. I'm going to plug in 0, pi, and 2 pi. This is going to leave me with a negative, a positive, and a negative, which again means my graph is going to be decreasing, increasing, and decreasing. So it's going down, up, down, which means somewhere between here it's got to change from going up to going back down. Or not change from going up and down, it's going to have to change concavity. And that point is going to be right here. Actually, we have changes in concavity on the ends as well. So let's see, if it's going down to up, what we know is that, let's go ahead and set, not really sure where this point is going to exist, so I'm just going to mark it generically here and say, okay, this is all going to be a nice little concave down. So I have a nice little concave down. It's decreasing. It reaches its minimum point, and then it's going to start increasing very, very slowly. At this point, it's going to change concavity from that concave up to a concave down, still increasing though, all the way up until this point where it hits its max. Then at that point, it's going to start decreasing, but it still doesn't change concavity. It would technically change concavity on the other end. It would change concavity on the other end, but we're not concerned about that. That is going to give us a good shape of what that graph looks like. And there we go.